Welcome to Ask and Learn.
All right, for this problem, we have a setup of how many positive integers less than 1,000, and then we fill in the ... differently for parts A through G, or rather A through H here. For part A, I'll actually introduce a little bit of notation just to make things a little bit easier to write. And let's say that the number of integers, or positive integers, less than 1,000 divisible by, let's say, m, I'll write as capital N of m, and then I'll use our logical notation for doing things like or and exclusive or. So, that being said, with that little bit of notation, for A, we want to find the number of positive integers less than 1,000 divisible by 7. So, all we need to do here is divide 999, because it's less than 1,000, not less than or equal to. Take 999, divide by 7. And we round that down. So we take the floor function. And that's going to be 142. For part B, we want to find the number that are divisible by 7 and not, oops, wrong notation, and not 11. So what we can do here is take the number of integers divisible by, the number of integers divisible by, one second here, the number of integers divisible by 7, and subtract off the number of integers divisible by 7 and 11. So, the number of integers divisible by 7 is 142. And the number of integers divisible by 7 and 11 is going to be the floor function of 999 divided by 77. Oops. It's a floor function, not brackets. And the floor function of 999 divided by 77 is going to be 12. So we have 142 minus 12, or 130. For part C, we're actually specifically asked, what is the number divisible by both 7 and 11? Which we already found, that was 12. For part D, we want to find the number divisible by 7 or 11. So the number divisible by 7 or 11 is going to equal the number divisible by 7 plus the number divisible by 11, which is going to be 142 plus the floor function of 999 divided by 11. Keep on turning those into square brackets by accident. And that is going to equal 142 plus 90. And then we need to keep in mind, one second here, we need to keep in mind that we will actually end up over-counting some, because there are, we already found out that there are 12 which are divisible by both. we're not completely removing those. Instead, we just need to make sure the 12 that are divisible by both are showing up in both those divisible by 7 and divisible by 11. So we actually need to subtract off the ones that are divisible by both. So that is going to give us 142 plus 90 minus 12 is going to be 220. For part E, we want to find the number divisible by 7 or 11, but it's an exclusive OR. Well, all we need to do is subtract off the numbers that were divisible by both 7 and 11 again. Keep in mind that those 12 numbers showed up or would show up in the list divisible by 7 and divisible by 11. So there are 12 that show up in both of those, which means that when we wanted to find just the ones that are divisible by the non-exclusive OR, or the inclusive OR, or divisible with the inclusive OR, we subtracted 12 once. We just need to subtract 12 again. So we'd have 220 minus 12, which is equal to 208. For F, we want to find the number divisible by the negation of 7 or 11. So we want the ones that are not divisible by 7 or 11. And that's going to be, well, there are 999 positive integers less than 1,000. And we had that the number of digits, or number of integers, rather, that are divisible by 7, inclusive, or 11 was 220, so we just need to do 999 minus 222, which equals 779. And for G, we want, and now this is a little bit liberal with my notation here, but I'm going to say n distinct. So that is the number, we want to find the number of positive integers less than 1,000, where each digit is different. So what we can do is think first about one-digit numbers. Well, all of those are going to be distinct, so we have 1 up to 9, so we have 9 so far. Then for two-digit numbers, we know that there are from 10 up to 99, or 90 overall, but we also know that there's 11, 22, 33, 44, 55, 66, 77, 88, and 99. So there are 9 without, or 9 which are not distinct, or 9 with repeated digits. So we'd have 90 minus 9 equal to 81. And then for the 3 digits, we can think about, we have from 100 up to 999. So there are 900 integers total. And then we would have, well, actually, we would have a easier way of dealing with the 3 digits case. What we can do is think about having 3 different holes that we need to fill. For the first hole, well, the smallest number that can go in there is going to be 1, and then we'd go up to 9. So we have 9 different choices. Then, for the next digit, the smallest possible thing that we can put in there would actually be 0, and we can go up to 9, so there would be 10 choices, except for the fact that we can't choose whatever we chose in the first place. So we have 9 times 9, and then for the last digit, we could have 0, and we just have the requirement we can't use whatever digit we used in the first 2 boxes. So we'd have 9 times 8, which is going to be 648. So, adding up all of the different possibilities, we'd have 9 plus 81 plus 648. Oops, 81, not 8. Plus 648, which is going to equal 738. And lastly, we have the number that have all distinct digits and are even. If something's even, that's equivalent to being divisible by 2. So, what we can do here is a similar counting method to in part G, where we start with the 1 digits. We know that there's going to be 2, 4, 6, and 8. So there are 4. Then when we look at the 2 digits, we would have all of the even numbers between 10 and 98, which there's going to be 45 overall. Then we need to keep in mind that there are going to be repeated digits in some of them. Between 10 and 98, the repeated digits, well, we would normally just think of, okay, well, 22, or actually it would be 11, 22, 33, 44, 55, 66, 77, 88, 99. But we are only looking at the even ones. So 11, 33, etc., those would not be considered. Instead, we would just have 22, 44, 66, and 88. So we would have 45 overall, and we would subtract off 4 of them. So we have 41 distinct and even with 2 digits. And then lastly, for the 3 digits case, we go into the different mode of thinking where we're thinking about filling in boxes. Now, any number is going to be even as long as the last digit is even. So, we end up with 4 different cases. Where we have going digit by digit, we would have odd, odd, even. I'm going to use O and E as short form for odd and even. We'd have odd, odd, even in case 2. We'd have odd, even, even. In case 3, we have even, odd, even. In case 4, we have even, even, even. Now looking at the odd, odd, even case, there are 5 odd numbers. So we choose one odd number, and then we have a limited pool of odd numbers to choose for the next digit. So we have 5 times 4. And then we choose an even number, so we have times 5, and we'll get 100 there. And then in the odd, even, even case, we choose from our 5 odd numbers. We choose from our 5 even numbers, and then we have 4 even numbers left to choose the last digit. So we again have 5 times 5 times 4, or 100. Then in the even, odd, even case, well, we'd have 5 to choose for the first digit. Or, excuse me, rather, we would have 4 that we can choose from the first digit. Then we would have 5 that we can choose for the odd in the second digit. And then we would have 4 that we can choose from in the final digit. That's because this first digit can only be between 1, or in this case actually starting out at 2, up to 8. And then for the last digit, 0 would also actually be a valid digit to use. So we have, even though we've removed one of the possible digits by choosing that first digit, we end up getting back one of the options, getting another option to make up for it, essentially. So we have 4 times 5 times 4. So we have 80 options there. And then lastly, we have the even, even, even case, where again, we have 4 options for the first digit. We'll have 4 options by the same logic for the second digit, and then 3 options for the final digit, giving us 48 possibilities. So the total number of 3-digit cases is going to be 328, And then we add on the 41 from the 2 digits and the 4 from the 1-digit cases. So the overall total is 373.